we're going to create the molecular orbital energy level diagram for F2 and the fluorine molecule. And I want to point out a couple of terms. One is homonuclear. It means that both the nuclei are the same, so it's fluorine and fluorine. The other thing that's going to be important is that there's a small 2s2px interaction, and I'll be explaining that later. So we're going to look at one of the elements that's on period 2 of the periodic table. So, you know, there's 1s and 2s, and you should know that there are 5 electrons on the p level of fluorine, both of them. Okay? So now how is the molecular orbital diagram going to look? Well, first, we're going to have our bonding orbitals. That's going to be sigma 1s, and then our anti-bonding, which is going to be sigma star 1s. We're going to do the same for the 2s. That's going to be sigma 2s and sigma star 2s. So let's move this down just so they're not interfering. Okay, so first we're going to fill up the sigma 1s. Okay, so one of the electrons comes from that on the left and the other one comes from over here on the right. Then we're going to do the same thing for the anti-bonding. Okay, so that takes care of both sets of 1s electrons from each fluorine atom. All right, then next we're going to do the same thing for our 2s. We're going to take one from each of the fluorine 2s's, put them on the sigma, the bonding, and then same thing for the anti-bonding. Okay, so far we have no bonds. Everything is canceled out. This is where it starts to get a little bit complicated. And so how do we put the order of the sigma and the pi bonds for fluorine? Okay, so this is how it goes for fluorine, and it's the same for neon and for oxygen. It's going to be the same pattern. In another video, I show you nitrogen. Nitrogen has a different pattern. Let me explain first how fluorine goes. So we're going to I'm going to put these in a different color. First is going to be sigma 2p. Next, we're going to have two orbitals that are both pi 2p. Those are going to be our bonding orbitals. For anti-bonding orbitals, we're going to start off with pi, so it's going to be the mirror image for fluorine. So this is going to be pi star 2p, and this is going to be pi star 2p. And then at the very top is going to be sigma star 2p. Okay? So let's start filling in. Okay, so we have 10 electrons we're going to put in here. So the first is going to go on the sigma 2p. The second is going to go on the pi 2p on the left, and then the pi 2p on the right. So we've used up 4. Then we're going to put another one on the left, pi 2p, and then another on the right, pi 2p, because those are the same energy, so we half filled those first. This was a lower energy, so we filled it before we went on to the pi. We filled the sigma. But in the case of these two, we half filled them because they're at the same energy. We're going to do the same thing now with pi star. So we're going to put an electron here and here. Okay, so that takes care of 2, 4, 6, 8. We have 2 more electrons. So we're going to go ahead and fill up the pi star 2p on both sides. That's the molecular orbital diagram for F2. So what I'd like to do now is draw the bond order. Remember, the bond order equals 1/2 of how many bonding electrons we have minus the anti-bonding electrons. We'll count those together in just a second. That'll give us the bond order. Now you should already know in your head from previous classes how many bonds there are between fluorine and F2. But let's go ahead and highlight. We'll do this color for the bonding. So that's 2, 4, 6, 8, 10 bonding electrons. So I'm going to put a 10 here. And then let's do the anti-bonding. 2, 4, 6, 8. We'll put an 8 here. So that's going to be a bond order of 2 times 1/2. So that means 1. And you should have already remembered that there's 1 bond in F2, which you remember from previous classes. So that's consistent with Lewis structure and Vesper and everything else. Now, the bond length is relatively long because of low bond order. So again, if we have a low bond order, we have a high bond length. Okay? What about the dissociation energy? Well, it is also relatively low. It doesn't take as much energy to break this bond, to dissociate, because its bond order is low. So if we have a low bond order, we're going to have a low bond dissociation energy. And so the bond strength is also relatively low. Again, same idea. Low bond order means low bond strength. Okay, so now let's go back up here to this issue right here. So what we want to pay attention to is the order that I have for these orbitals. Okay, those are the tricky ones. So it is this pattern, 4, O2, F2, and N2. That's the pattern. So this is first. That sigma 2p is first. However, it's not that way for all of the level 2 elements. So let me show you. This is higher, and this is the pattern. You see the sigma 2p is higher. Pi comes first. So this is what I'm telling you. Pi first. And this is the pattern for boron, carbon, and nitrogen. Pi comes first. Sigma comes first for oxygen, fluorine, and neon. Sigma is at a lower energy level. But for boron, carbon, and nitrogen, pi is at a lower energy level. Now here's how I remember that. I love bacon. And you know what? I love bacon so much. I would love a bacon pie. So that's how I remember it. Kind of silly, but for bacon, pi comes first. Just remember bacon pie.